Well, friends, we have discussed dielectrics, the different materials called as conductors, insulators or dielectrics and semiconductors, polar and non-polar molecules. Somewhere we have stopped saying about polar molecules and non-polar molecules. Well, if we have a polar molecule or a polar substance and say this polar substance is placed in an electric field, what happens when a polar molecule or a polar substance is placed in an electric field of suitable strength? The molecules experience a torque. All the molecules, in the absence of electric field, they are randomly oriented. Due to the random orientation, the one molecule exerts a force on the other. Because of the internal, say, forces, the net dipole moment of the bulk material for a polar dielectric substance is zero, though the individual molecule has a dipole moment. Now, such a material or a substance, when it is placed in the presence of electric field, polar molecules in the presence of electric field, if say E0 is the applied electric field and say the molecular dipole moment, the polar molecules, as we know, they have the permanent dipole moment, and the permanent dipole moment of a molecule, that is a polar molecule, is P, the polar molecule dipole moment. See, these polar molecules, they get acted or they are acted upon by a torque. A torque will be exerting on each molecule, and torque is equal to the P cross E. P is the dipole moment, that is permanent dipole moment, and E is the E0 is the strength of applied electric field, or here it is electric field intensity. It's a cross product of two vectors, is a vector, and this torque is exerting on each molecule. Torque aligns or tends to align the randomly distributed dipole moment in a bulk, and after the alignment, depending upon the strength, the alignment will be complete or partially. The quantity which is responsible for the alignment of each molecule in the direction of applied electric field is torque. Torque is equal to P cross E0, and this torque tends to align the molecules partially or completely, and the picture will be inside the sample or a bulk of polar molecule substance known as a dielectric will be like this. All the positive charges will be aligned on one side, all the negative charges will be aligned on the other side. We say here the polar molecule is electrically polarized. Polar molecule is electrically polarized, or we say electrical polarization takes place. We are familiar with the word polarization, polarization of light, the concept polarizability, and then different types of polarization, plane polarized light, we have elliptical polarized light, we have circular polarized light. This polarization doesn't mean only for the light. We get here that kind of things in electricity, we call it as electric polarization. Commonly this word polarization is used in day-to-day life, that is even in election process. People say that votes gets polarized, they get concentrated on one side. So we use the term here called as electric polarization. The physical meaning of electric polarization or physical meaning of electric polarization in dielectric. Here we are concentrating on dielectric. Physical meaning of electric polarization: when the molecules of dielectric, say polar or non-polar molecules, are aligned completely or partially in the direction of electric field, the dielectric or dielectric molecules or polar molecules are said to be polarized. Now the question is, how to measure this polarization? Polarization is measured in terms of a quantity called as electric polarization or polarizability. When we talk about the electrical polarization, if you are talking about the atoms, it will be atomic polarizability. If you are talking about the molecules of dielectric, it will be molecular polarization. In general, this polarization is microscopic phenomena, and we take the overall at macroscopic phenomena. So here molecular polarizability is a microscopic phenomena, atomic polarizability is microscopic phenomena. But when we put a substance under electric field called as polar molecule substance or dielectric, it aligns all the molecules. The alignment is done by torque. Now, this polarizability or electric polarization depends upon two factors. One, the strength of electric field. Larger the electric field, greater will be the polarizability or larger will be the polarization. All the molecules, they perfectly get aligned in the direction of electric field, and here the dipole moment is known as the induced dipole moment, and the direction of this dipole moment is parallel to the applied or external electric field. They are parallel to each other. The one thing, this polarizability or polarization in dielectrics depends upon the strength of electric field, external electric field or applied electric field. The other quantity on which this electrical polarization or polarizability depends is the thermal agitation. Thermal agitation. What do you mean by thermal agitation? We all know atom about its mean position starts vibrating at certain temperature. When the atom is at a ground state, we say it is stable. When the atom is not at ground state, or when it is inside the bulk, a sample or a dielectric material, fine. That sample or a dielectric material, when it is at room temperature, at absolute zero it will be different, and at room temperature the different pictures you will see. All the molecules, they vibrate about their mean position, and they acquire what is called as a thermal energy or thermal agitation. And this thermal agitation to certain extent opposes the polarization here. So smaller is the temperature, greater is the alignment. At Lower temperature, the alignment of dipole moment or polarization is better. So, depending upon these two factors, what is called as electric field intensity or field strength and thermal agitation, we calculate the polarizability, electric polarization, we measure it. And always the electrical polarization is the strength of electric dipole moment per unit volume is directly proportional to the strength of applied electric field. If E0 is the external applied electric field and if P is the dipole moment, that is total dipole moment, what is called as including induced dipole moment, P is proportional to E0 provided that temperature is constant. At a given temperature, P is proportional to E0. When I write this as P is equal to, say, some constant of proportionality epsilon naught into E0, or epsilon naught is equal to, this proportionality constant alpha here, not epsilon naught, alpha is equal to P by E naught. And this is known as atomic polarization or atomic polarizability. When we take this or when we study this at atomic level, it is called as atomic polarizability. Atomic polarizability of a dielectric material is defined as it is electric polarization which is directly or the dipole moment per unit strength of electric field. It's a ratio P upon E naught for a given unit electric field. P is equal to alpha, what is called as atomic polarizability or atomic polarization. Well, P upon E naught. Let us see the same concept in case of non-polar molecule. We know when we have a non-polar molecule like this, the center of gravity of a molecule, that is a nucleus here, you can take atom and then nucleus. The center of gravity of a positive charge called as nucleus is coinciding with the center of gravity of negative charges. We have not seen this and it's not possible for us to see this. Say we can imagine this is a nucleus of positively charge Z into E, and there is a cloud as we have seen even in earlier class here, and this cloud is, say, circular one. Together I have drawn this nucleus as well as the electron cloud. So the electron cloud is having negative charge. The center of gravity of a negative charge is coinciding with the center of gravity of positive charge. They are coinciding on each other. So this is a positive charge, this is negative charge, and we know that atom as a whole is neutral. Fine. So when this is the situation, there is no separation between positive and negative charge. In case of non-polar molecules, the net dipole moment per unit volume is 0. The dipole moment P is equal to 0 in case of non-polar. That is, when that non-polar substance or a molecule or a non-polar atom is not placed in electric field. Let us see when a non-polar dielectric sample or a bulk material when it is placed in electric field. Imagine these are the vertical lines I have drawn which represent strength of electric field and its direction. It is top means bottom to top. This is negative side and say this is positive. It is acting in this direction. So this sample, this molecule, when it is subjected to electric field, the center of gravity of positive charge and the center of gravity of negative charge, they relatively displace from each other. Look, here is this inner circle is the center which represents, here is the center. If you see the figure carefully, this is center of positive charge, that is center of gravity of a positive charge, and here this is the center of gravity of a negative charge. I have written center of gravity of a negative charge. These two charges get separated. See, the electric field is assumed to be acting in upward direction from bottom to top here. This positive charge gets displaced along the direction of electric field, and the negative charge or the cloud called as electron cloud get displaced exactly in opposite direction, that is in negative direction in a bottom side. So they get displaced here. And what is the displacement between these two? I have drawn a small sphere here. R, if small r is the radius of the sphere which separates the positive charge on the circumference and negative charge at the center of the small sphere here, and r is the distance between them. Now, this is the picture you can see or you can experience when that sample dielectric non-polar dielectric substance is placed in an electric field of suitable strength that induces here both the positive and negative charges. The center of gravity of positive charge and negative charge coincides and the dipole moment is zero. Here in this case, that is in the presence of electric field, they get displaced relatively, they get displaced. One moves in the direction of electric field and the other moves, that is negative charge, moves exactly opposite to the direction of electric field. Anyway, they get displaced. The displacement between two causes a dipole moment. Say this is a positive charge plus q, and say this is a negative charge minus q. They get displaced from each other, and that distance is say dl. However small the distance is dl. Now, the product of either this charge q into dl causes the dipole, creates the dipole, and that dipole is known as induced dipole. This is induced dipole. And the moment called as dipole moment is induced dipole moment. QDL is the dipole moment called as induced dipole moment. Now, this dipole and the dipole moment last for a time as long as this applied electric field is there, the dipole moment exists. Moment we remove or switch off the electric field, that is voltage per unit length or voltage per unit area, that's volts per unit length, that is the electric field we call it as a strength, electric field intensity or its strength. When we take it off, the dipole moment disappears. As long as the electric field is present and say suitable electric field is present at a given temperature, you can say this dipole moment will exist. It will disappear moment we withdraw what is called as electric field. Now that I have written here, this is minus Q plus Q. Say this is nucleus is having positive charge Z into E plus ZE, and the electron is having Z into E, that is a charge here. So the plus Q minus Q, the separation between two, that is dl, we get T is equal to Q dl, the dipole moment, which I have written here. Now, how do we calculate this dipole moment? Magnitude of this induced dipole moment can be calculated, can be obtained using this figure here. If r is the capital radius of this sphere, small r is the radius of this sphere, which we have taken the distance as the radius here, distance between positive and negative charge, we get charge into distance. Charge may be charge of electron, Z is atomic number of particular sample or the atom, E is the charge, right? If it is positive for a nucleus, it is negative for electron, R is the distance. And this is the magnitude of induced dipole. And when we take a dipole moment, which is a vector quantity Q into dl, it is acting parallel or along the direction of applied electric field. When you calculate that in terms of this capital R, the radius of the atom or the say here atom, okay, 4 pi epsilon naught R cube into E naught. Or from this you can say the electric dipole moment, induced electrical dipole moment is say proportional to E naught. Somewhere I have written that is P is proportional to E naught, or it is equal to alpha times E naught, or alpha is equal to P upon epsilon naught. In case of polar molecules or in case of non-polar molecules, the induced dipole moment called as atomic polarizability, alpha is the ratio of the induced dipole moment per unit electric field. If we apply unit value of electric field per unit field, then we define the dipole moment per unit field is called as atomic polarizability. This atomic polarizability can be calculated, can be measured in terms of this, the unit of what is called as units and dimension of say atomic polarizability. Polarization called as electric polarization, that too in dielectric, and units and dimension of alpha here. Alpha, atomic polarizability, atomic polarization, that is equal to P, the dipole moment, and dipole moment we measure charge into meter, coulomb into meter. I have written coulomb into meter per volt per meter. Volt per meter is the unit of electric field. So if you simplify coulomb meter square per volt, we know the unit of capacitor is a farad. Farad is the unit of capacitor, that is coulomb per volt. and here it is coulomb per volt. Farad into meter is the SI unit of say atomic polarizability. Farad per meter or coulomb meter square per volt is the SI unit of say atomic polarizability, or you can say molecular polarizability. When we discuss that molecular polarizability, we will write its unit. What is the dimension of this? The dimension of dipole moment, that is charge into distance, Q into L, we write, and force per unit charge, right? We write force is L T raised to -2, Q is -1. Alpha we have here charge into distance, coulomb into distance divided by volt into meter. So this will be voltage here, M L T. This is P. You can say Q raised to -1. When you simplify, the dimension of atomic polarizability M raised to -1, T raised to 2Q square, and this is the dimension of atomic polarizability. What else we have to discuss in this? Once we are familiar with what is called as electric polarization, either it is in polar substance or in non-polar substance, electric polarization, and then dipole moment, atomic polarizability. So this dipole moment meant P. Dipole moment, we call it as density of dipole moment or density vector. Density of dipole moment. It's a vector quantity. Dipole moment is a vector quantity, and always it is acts in the direction of electric field, either in electric dielectrics. It acts in the direction of electric field, so that they are parallel. If E is the or E naught is the external applied electric field, and say P is the dipole moment, both are parallel to each other. It always acts, and therefore we say that P is always proportional to E, electric E naught, and then we calculate that alpha, the atomic polarizability, that is P upon E naught. Dipole moment is a vector quantity. We can somewhere we come across the density vector, dipole moment, density vector. And say it is P. This dipole moment density vector can be related to surface charge density. Surface charge density. So in dielectric, when the dielectric sample is placed in electric field, we get two kinds of charges. One, in polar molecules, sometimes we get free charges. In non-polar molecule, we get, say, induced charges. So there are two types of charge densities here. That is charge density due to free charges and charge density due to induced charges. So this quantity surface charge density is related to the dipole moment, or dipole moment can be expressed in terms of surface charge density. Let us see how they are related with each other, and that we can discuss in the next video or in the next online class. Bye. Thank you.